Hello, and welcome to Let's Meet the Virologists, a podcast about the people behind today's virology headlines. People just like you working to understand viruses and how they affect you. During the COVID-19 pandemic, we are talking with researchers involved in coronavirus and COVID-19 related research so that you can learn who they are and what they do. I am Larissa Thackeray, and I am hosting this podcast from America's Heartland in St. Louis, Missouri. While SARS-CoV-2 was initially thought of as a virus that only causes respiratory disease, on March 1st, 2021, we talked with Dr. Adam Bailey, a clinical pathology fellow in the Diamond Lab, and Sasha Dmytrenko, an MSTP student in the Levine Lab at Washington University School of Medicine in St. Louis, about their work to determine how SARS-CoV-2 can cause cardiovascular disease. Sasha received his bachelor's from St. Olaf College in Minnesota. Adam receives his MD PhD at the University of Wisconsin-Madison School of Medicine and Public Health, where he studied PEGI and arteriviruses. He then completed his medical residency and postdoctoral fellowship at Washington University School of Medicine, studying yellow fever virus and SARS-CoV-2. He is currently recruiting for his own lab at the University of Wisconsin-Madison to study the pathogenesis of viral hemorrhagic fever and persistent RNA virus infection, as well as emerging viruses. Thank you for talking with us today, Adam and Sasha. Why don't we start with Adam? Why don't you tell us a little bit about yourself and how did you become interested in virology research?
Okay, well, I'll give you the condensed version. My name's Adam Bailey. I was born in Salt Lake City, Utah, and both of my parents were physicians, and they would talk at the dinner table about all sorts of nasty stuff that they did all day. And this really instilled an intense fear of germs in me from a young age. And so I was, I guess what you would call a typical germaphobe. But it kind of had this weird moth to the flame effect with me. And as I got older, I became more and more curious about microbiology and had my first laboratory experience just by emailing a professor. Our family moved to upstate New York, Rochester. And so my first experience was after my freshman year in college in a virology lab in Rochester with Dr. Stephen Dewhurst, and I kind of had always thought I wanted to go to medical school, but then I got hooked on research, and so I decided to just do both. And so then I did MD PhD at Wisconsin, and now I'm finishing up my residency in pathology and postdoc with Mike Diamond at Wash U in St. Louis, and now I'm very excited to be going back to Wisconsin to start my own lab starting in July.
Cool. And so Sasha, how about you? How did you tell us a little bit about yourself and how did you become interested in virology?
Hi. My name is Sasha Dmytrenko, and I was born in Kyiv, Ukraine, and moved to United States only almost 8 years ago, actually, to go to college. Was not interested in any of the bugs or pathogens. I do not have virologist parents, but which is actually not true. My dad did virology research, as it turned out later, but that did not really affect me growing up too much. But I joined Corey Levine's lab here at Washington University in St. Louis as part of my MD PhD training to study effects of immune system on the heart, and again, still was not interested in virology or pathogens, but then started collaborating with Adam to look at effects of SARS-CoV-2 and COVID on the heart. And that was very interesting. And knowing that Adam was moving, I decided to get trained. And now I guess I'm a virologist.
It just takes working with one to be one. It's a very low bar.
They're infectious.
Yes. So Okay, well, let's get right into that. So I've actually been wanting to talk on my podcast with people who are studying SARS and not necessarily monoclonal antibodies or vaccines or what have you. So this is that's partly why I wanted to talk with you guys. It's like, let's talk about studying sort of some of the other things that SARS does. So Sasha, why don't you just start with, how did you get into studying SARS-CoV-2 and the heart?
Yeah, so that's definitely not something I feel like everybody thinks about, especially early on, that heart was not the organ that people thought about. But being in a cardiology lab, it was very clear early on that there were some reports coming from Seattle when that was the epicenter of the outbreak in the United States, that there were patients who had heart issues who were also COVID positive in the ICU. But the biggest question was, it was not clear whether that was a direct effect on the heart by the virus, or whether it was just a hyperinflammatory state, a total body collapse that then manifested in a cardiac problem. So that was a big question that we wanted to address, and that's how my PI, Corey Levine, started collaboration with Mike Diamond, and we were connected to Adam.
Right. So Adam, why don't you kind of take us through that? So like, how did you guys, I know you were involved, obviously, setting up the first mouse model and some of those initial studies, but how did you start thinking about how to look at SARS infection and the heart? Sort of like what Sasha was saying. Is it a direct effect? Is it an indirect effect? How did you think about that?
Right. So I've always been interested in pathogenesis, which in other words is, how does the virus actually cause disease? And so early on during the COVID-19 pandemic, I was heavily involved in trying to figure out what sort of animal model systems to use to study this question, pathogenesis. And like with many infectious diseases, it's actually very hard to recapitulate the human condition in an animal. So, for example, when you look at the risk factors for developing severe COVID-19, the main ones are age, to a lesser extent sex, but then other comorbidities like cardiovascular disease and diabetes and obesity. And those things are essentially impossible to model in a 6-week-old mouse, or really any animal model. And so during that time, Corey approached Mike and said, hey, we've got this cool cardiomyocyte in vitro system, and we do some stuff ex vivo from patients. Are you interested in collaborating? And Mike said, Adam, this sounds like your cup of tea, so why don't you go talk to him? And I remember going to his office and sitting with him and Michael Greenberg, who was the other PI, who was more of the biomechanics guy, who sort of artfully creates these engineered heart tissues that we ended up infecting. And I just remember being exhausted and burned out, but what they were selling me was actually pretty cool. And so I said, all right, well, I'll give you one experiment. I'll try and infect these pluripotent stem cell derived cardiomyocytes that you have. And I, was betting that they wouldn't work, because at that time we were just kind of testing lots of different things and nothing was working. But they got infected. And so right then I thought, well, that's odd and could potentially be interesting and useful. And so we started doing some experiments characterizing infection of these pluripotent stem cell derived cardiomyocytes in vitro. And then from there, we were able to build out and start to look at whether or not cardiomyocyte infection occurs in humans. Sasha is now developing some animal models to try and model direct infection of the heart. in an animal. But, you know, for me, there were a couple papers early on that not only clearly demonstrated that cardiovascular disease was a risk for severe COVID, but the fact that people who died of COVID had significantly elevated troponin levels, which is an indicator of heart damage, compared to those who got COVID but did not die. You know, that was kind of another red flag suggesting that, you know, something's going on in the heart, and we should probably start studying it. And subsequently, we've kind of learned that direct infection of the cardiomyocytes, you know, may happen, but certainly not to the extent that we're seeing in these pluripotent stem cell derived cardiomyocytes. So again, no model's perfect, but some are useful. And so continuing to come at it from multiple angles, and you know, maybe Sasha can pick up the story because it took an interesting turn recently that he's been working on primarily.
Great. Yeah. Why don't you tell us about that, Sasha?
Yeah, so we started with focusing on the cells of the heart muscle itself, so the cardiomyocytes. And recently, in collaboration with Stacy Rentschler's lab, we found that pericytes can get infected. And pericytes are these cells that are important for maintenance of blood vessel and the endothelial barrier. They're mostly studied in the brain in the context of blood-brain barrier. So they don't make the barrier itself, but they're the housekeeping cell that makes the other cells happy around them in the blood vessel. And our preliminary data suggests that the cardiac, specifically primary cardiac pericytes isolated from a human heart, can get productively infected with SARS-CoV-2. And that is very interesting because this also can contribute to the component of the disease that is widely described with all the vascular issues. So not only the heart problems, but the coagulation issues in the blood vessels, like microemboli and things like that.
Right. And Adam, to follow up on that, isn't that something that you're interested in studying as well, as sort of coagulation and how viruses affect that? So I know you've published recently on yellow fever virus, which is a completely different virus that also causes different coagulation. But is that something that you're interested in following up on?
Yeah, so this is an area that I'm choosing to actually start my lab centered around, is this idea of interplay between viral infection and abnormalities in the coagulation cascade. And for a long time, people have essentially thought that coagulation in severe viral infections like Ebola virus, for example, is due to aberrant activation of the immune system, a quote cytokine storm, if you will. And I think that's actually done the field a great disservice because it essentially is a very vague and hand-wavy explanation for a phenomenon that is very important for disease. And so I'm trying to come at this problem from the perspective of somebody who understands the coagulation cascade and some of its complexities based on my clinical training, but then also has the ability to go into a high containment lab and work with viruses. And so the more I've started to read about this, it's actually quite fascinating. And there are many different flavors of coagulation abnormalities. So what we see in Ebola virus and yellow fever, for example, is a very fulminant process that's not only characterized by the formation of clots, but also characterized by bleeding abnormalities in those people, like fulminant bleeding abnormalities. You know, you think of the Ebola patient of bleeding out of their eyeballs or whatever.
Yeah.
COVID is interesting because it was shown early on that another strong predictor of disease severity and outcome with COVID is this molecule called D-dimer. Now, D-dimers, so in the blood clots, the clots essentially fall out of solution, right? They kind of lodge where they're activated and they start forming. And so you can't really measure a clot in someone's blood. And so if that person is bleeding, you don't know if they don't even have enough clotting factors around in their blood, or if they're actually experiencing an activation of their clotting cascade and they're consuming all of their clotting factors, and that's why they're having a bleeding problem. So the way you tell the difference between those two is with this molecule called D-dimer. And this is formed when clot is remodeled by an enzyme in the blood called plasmin, and it releases this little peptide from the clot that we can measure, and that's called D-dimer. So yellow fever patients have very high levels of D-dimer, which I recently showed. Ebola victims have very high levels of D-dimer. They also have bleeding abnormalities. COVID patients have very high levels of D-dimer, but they do not have fulminant bleeding abnormalities. So this is sort of a different flavor of a coagulation abnormality where clearly there's some degree of clot formation and turnover, but it's not enough to cause a full-blown coagulopathy where all of their clotting factors are consumed. It's more of a smoldering sort of coagulation disorder. Still abnormal, but we don't understand how any of this works. So it's been very difficult to tease apart. And, I was interested in studying this and had the idea that, maybe endothelial cells are directly infected and their dysregulation is then activating, causing D-dimer formation at a low level. And the literature, some of my preliminary experiments, but also the broader literature has pretty much demonstrated definitively that endothelial cells do not get infected. However, if you imagine that endothelial cells are very tightly regulated by a cell that lies directly underneath them, and that if that cell gets infected and the endothelial cell then becomes unhappy, you could essentially imagine a similar effect. And so that's what we're thinking infection of pericytes might be doing. And it could explain a lot, everything from, yes, the coagulation abnormalities that we're seeing in COVID, but also the blood pressure dysregulation and this sort of long COVID, long hauler COVID type syndrome, or even MIS-C in the kids. So, if you look in PubMed, there's maybe like 20 papers on pericytes. So it's a really underexplored aspect of biology in general and viral tropism in particular.
Cool. And Sasha, could you give us a little idea of how you're going to be, what kind of like mouse models, or how else are you going to be studying this? So it sounds like it's kind of complex, obviously, to study the various aspects of it. So how are you going to move forward with it yourself?
Yeah, so there are a couple things we tried, and the biggest, I guess, the biggest barrier that I will have to start with is that a mouse does not get infected with the wild type SARS-CoV-2 due to the difference in the sequence of the binding receptor, the ACE2. So, which is a blessing and a curse in a way. It's definitely a blessing because we did not need to worry in the beginning of the pandemic about the colonies getting infected and being the reservoir, but then it also makes it harder to study. So one of the approaches that we have started with was using a backbone of a different virus, adeno-associated virus 9, which is known to infect a number of tissues, including muscle and specifically heart muscle cells. So we used that as a backbone to put human receptor sequence for SARS-CoV-2 into it, so human ACE2. And we specifically engineered it to to be under the cardiac troponin promoter. This was done by David Curiel's lab, to then express the receptor only in the cardiomyocytes of the heart. So this work is ongoing, and definitely there are a lot of improvements to be made with this model, but that's kind of where we are at. And there are many other alternative approaches that one could try, but this is where we started.
So do parasites express ACE2, human parasites?
Yes, they definitely do.
Okay.
Yeah.
Okay. Interesting. And so I guess what's the next step though in your, so if these cells are infected ex vivo, as it were, what's next?
Yeah, so I think for me, the exciting part is the mouse model, because it allows us to study a full immune response to an infection, because the biggest limitation of an ex vivo or in vitro approach is you only can study what you put in.
Right.
Currently, based on our very preliminary data from the mouse and also our human autopsy and biopsy imaging, it looks like the immune infiltration into the heart is very unique for a myocarditis case. So that will be very interesting to dissect that in a mouse model, because the primary focus of the lab, where I'm at with Corey Levine, is at cardiac macrophages, being the most predominant immune cell population in the heart. So if this model holds true, just like what we see in the human, which the primary infiltrate is macrophage based, it will be really interesting to ask mechanistic questions of what those cells are doing, why they're doing it in response to this viral infection, how is that different from other infections, and so on.
Cool. And Adam, how about you? What's next for you? It sounds like you might be actually doing some SARS research in your own lab. What's the next thing for you?
The next thing for me, well, I'm trying to get my lab off the ground at Wisconsin, while still maintaining an active research program at WashU. And so I'm in a bit of a transition phase where I'm doing everything at once, so nothing really gets done. But yeah, I'm interviewing people for positions at all levels. I'm making sure all my protocols are in place so that I can do things when I get there without having to delay further.
Yeah.
So yeah, I also have 2 little girls, and my wife is currently running the gyne oncology service at the hospital. So I'm pretty much single parenting right now. So so that's what I'm doing with my time. Yeah. Helping Sasha as he needs help, but he increasingly does not.
So I guess maybe talking more generally about science and what have you, what has been the most exciting moment in your career so far?
I think on like pure emotional level, one of my summer rotations during my undergrad training was with Tim Nelson at Mayo Clinic, whose lab focuses on induced pluripotent stem cell derived cardiomyocytes as models for this rare congenital condition called hypoplastic left heart syndrome. But I just remember when I was there, I learned how to do a differentiation of these cells into the cardiomyocytes. And the coolest thing about the induced cardiomyocytes is they beat in a dish. And I just remember how, without any cell culture experience coming in, after you like finish a month-long differentiation protocol and this thing starts beating in a dish, it's just like so crazy and exciting. And yeah, I remember that day when I came, I think it was like a Friday night, I came into the lab to check on them, and they're like, I think, and they don't do it very frequently or very rhythmically, especially when you take them out of warm incubator. If you don't look at them right away, they kind of slow down. And I was just like, did that just happen? And it did. It was so fun.
Cool. And conversely, what's been the hardest thing you've had to overcome in your science career so far, and how did you overcome it?
That's a great question. I think finding a balance between doing things and like thinking about big picture questions has been the hardest, definitely. Have I overcome it? Well, that's probably, I'm working on it. Yeah, trying to schedule regular time to do that, I think, is my current approach. Again, is it working? I'm not sure it's for me to judge.
How about you, Adam? What's been the most exciting moment in your career so far?
Yeah, I was thinking there's several that come to mind. I think probably the most exciting moment was I spent a lot of my PhD trying to make an animal model for this virus called human virus, which infects a lot of people around the world, but doesn't really seem to cause disease, and nobody really knows anything about it because there's no systems to study it. And I happened to be part of a team that discovered the first baboon virus in Africa during my PhD. And I wanted to see if, because baboons and macaque monkeys are more closely related to each other than humans and macaque monkeys, if macaques would be susceptible to infection with a baboon virus. We know they can't be infected with a human virus. And so the day that I got the viral loads back and they actually were positive was pretty cool. Creating the first model for something, to study a totally opening all these doors to study things. And then, we had basically infected these monkeys with neat baboon blood. And then a couple of days later, one of the monkeys died. And so we freaked out because we thought so it went from elation to being very nervous because we thought, well, maybe there's, we screen for all sorts of other pathogens, but you can never be 100% sure. And then it turns out the monkey had like cancer that we didn't know about. So totally unrelated. But so that was really exciting. I mean, there's the thing about science, and this I guess relates to the next question you're going to ask me, which is, what has been the biggest challenge? Is it's such a roller coaster. You have extremely high highs, the thrill of discovery, making a difference on an important problem, COVID, hemorrhagic fever, for example. But, most of your time is spent dealing with rejection or failure. If 10% of your experiments work, that's pretty good. If 10% of your papers get into the journal that you initially submitted to, like, that's great. Grants getting rejected. It's like a inherently, it's not a process that's really meant to build you up. And so, it teaches resilience, I think, for sure, but it also, doesn't come naturally to everybody. And it's certainly kind of like a learned trait to just let it roll off your back and not take it personally. And it's taken me a long time to get to that point, but it also is once you get to that point and you can just shake off failure, it's actually really, it translates into other parts of your life as well. And so I think, ultimately that's a good thing, but it's tough, just constantly being told like, your work isn't good enough or your ideas aren't good enough. It stings, and it still does, but it's, I have some coping mechanisms now to help, not take it personally.
So I guess my follow-up question is, and I guess we'll start with Adam, is if you had a chance to ask your older self, so say you close to retirement, 70 years old, one question, what would it be? What would you want to know?
I guess I'd want to know, did I spend enough time with my kids? Because at the end of the day, I mean, I go out of my way to spend quite a bit of time with my kids. So I guess I could be asking myself, should I have spent more time at work? But I don't think, I have that fear that like, I'm going to be an old man and wish I had spent more time with my kids, Cat Stevens song, haunts me.
Sasha, what about you? What would you want to know?
I think I would want to know what, I guess probably a very generic, not generic, but broad response, but kind of with the hindsight, what would I do differently about, like specifically probably about the science training.
Okay, so I guess just finishing up, we're now like almost a whole year into the pandemic. I still remember last, for me, the pandemic became real spring break of last year in a way, because we couldn't go on spring break. So how have you dealt with the past year? How has it affected you? And kind of how do you see things going forward in the next couple of months? I guess, Adam, I'll just start with you.
Yeah. I think it's affected everybody a lot. It's probably affected me less than other people because I still came to work every day because, I switched, I wasn't working on my typical projects. I switched to working on COVID, but, the day-to-day stuff was kind of the same. I think the hardest thing has been, my 3-year-old daughter, when the pandemic started, is now 4.5, and she kind of knows what's going on, and she now refers to this magical time in the future when, quote, when virus is over. Like, when virus is over, like, can we go do this, can we go do that? And it's just like heartbreaking to hear of like a 4.5-year-old ask me, did you hand sanitize her, Daddy? Did you make sure to use the hand sanitizer? And so that's been kind of emotionally difficult.
How about you, Sasha? How has the past year changed? How did it change for you, and sort of where do you see us going?
So I think, the year has been, as Adam said, it affected everybody. And again, clearly not as much people who could keep working, even if the projects change. But I think, surprisingly for me, on a personal level, I think the biggest discovery of the last year was actually that I do need time alone more than I have ever thought I did, which I think a lot of people would expect the opposite, that you discover that you need human interactions. But I knew that part for a very long time. So this was an interesting and completely unexpected finding for me. I think the hardest part was not being able to see people in the same way, and specifically not being able to see my immediate family and go back to Ukraine for like over 1.5 years at this point. Going forward, hopefully some of the things soon enough are going to roll back, in a safe way to some extent due to vaccination being deployed on a pretty large scale.
How did you both sort of think about or deal with vaccination? Because I think a lot of people sort of that listen to the podcast are sort of they're not vaccinated yet themselves. How did you think about that? How was the process for you all?
Yeah, so I think it's a great question, and I think just the same way as you said, we're ahead of the curve on getting it. Also, it does help to have this background in understanding a lot of these things that just like rapidly came out to a better extent. I think so. It was impressive how all the studies that came out, how effective they were, and I guess was a no-brainer for me from that perspective. I do understand though that it does seem very odd, especially for people who have never seen how a vaccine rollout happens or never watched it this closely. I've never watched it this closely before either. So I think trusting the science that shows good effectiveness from all these outcomes that we do not want to happen, such as severe complications, hospital stay, and death, was what convinced me, combined with a very very minor side effect profile.
Yeah.
And remembering that most common things that do happen after vaccination are actually signs that the immune system gets activated rather than the true unintended side effects.
Right.
Things like soreness and achiness, even fever,
Right.
happen not because you get infected, but because your immune system thinks that it has to build a response to something. So,
how about you, Adam? I mean, thinking more about, say, your kids, vaccination in general. What did you think about the whole process, or taking it where you see us going for vaccination?
Yeah, I mean, I was, standing outside of the vaccination clinic at WashU every day asking for leftovers to see if I could get it before it was my turn, because that's how much I think it meant to me. I wish my kids could get it now. Clearly the FDA has a fine line to walk in terms of making sure the vaccines are safe so that, we can increase our confidence in these things, because there's already so much bad information out there. We don't want to give those groups and people that are anti-vaccine actual ammunition in the form of a bad vaccine. So we don't want to do that. But at the same time, I do wonder if, some of these regulations should be made more on a platform basis, as opposed to like each individual vaccine for each disease, each pathogen or whatever. Because this is not the last time that we're going to see a pathogen emerge like this. And if a year is record time to get a vaccine, that's still not fast enough. And so I don't know what the right answer is, but I think there needs to be some serious reevaluation of, going forward, if there were to be an outbreak of disease XYZ, like what are the minimum essential things we need to do, and how can we optimize dosing ahead of time based on the platform so that we don't have to do all the things that we know are going to be safe and going to be effective. Do as much as we can ahead of time to make sure that we can roll out a vaccine even faster next time, because the anti-vaxxers aren't going to go away, but we need to protect the healthcare workers and all the other people who genuinely need it to do their job and can't just rely on staying at home to stay safe. So, yeah, I mean, ultimately, the vaccine gives you better immunity than infection. So the people who don't get vaccinated are just going to keep getting COVID.
Yeah. I mean, it's always difficult. It's, there's all these questions of safety, there's some historical hesitancy, trust in government, things like that you have to overcome as well. So
yeah, and vaccine hesitancy isn't just like one block of thinking. Like, each group has its own specific factors, and some of those are more justified than others, but understanding each one of those is important. And something else I've been disappointed with is I've seen virtually no advertising by the government to try and make people aware of the vaccines, starting conversations around that. I mean, they invented the PSA. I mean, like, what happened? I don't know. That's, all of Dr. Seuss's initial, anti-malarial campaigns and stuff like that was for the CDC. Why aren't they doing stuff like that? I don't know. It's been a really disappointing leadership failure at multiple levels, but, all we can do at this point is learn from it.
Yeah. And try and do better next time.
Yeah.
All right. Well, thanks so much. I appreciate talking to both of you. Good luck with your setting up your lab, Adam. I'm sure we'll hear good things. And Sasha, I'm sure we'll be talking about mouse models still for quite a few months, years to come. Adam and Sasha's work has uncovered a potential role for parasites in COVID-19 disease. Sasha will continue these studies at Washington University, while Adam will study SARS-CoV-2 and other viruses in his own lab starting this summer. This has been Let's Meet the Virologist, a podcast about people who study viruses. This is your host, Larissa Thackeray, and thanks for listening. You can find us on Google, Apple, Amazon Music, Spotify, and other podcasts, or at lmtv.podbean.com. If you are a virologist interested in sharing who you are and what you do, please contact us at letusmeetthevirologist@gmail.com.